Hello everyone, this is Sir Aris. We'll talk about determinants and Cramer's rule. The determinant of a square matrix A, denoted as determinant or det A, can be indicated by replacing the parentheses by single bars. So you have this parentheses that we usually have for our matrix. We replace them by single uh, bars that would denote that we are taking the determinant. The value, for example, for a 2 by 2 matrix of this matrix A is simply A times D minus B times C. Um, for an nth order matrix, let's say we write the determinant like this. Um, the first subscript, so here in the subscripts shown, so we have here 1 1 1 2 1 3 and so on. So the first subscripts is 1 1 1 here, and here we have 2 3 and n. This corresponds to the rows. And the second subscript 1 here, this becomes 2 here, 3 and n corresponds to the columns. So for an element aij is in the ith row and jth column. As an abbreviation for the determinant, we write simply aij as the determinant whose elements are aij. If we remove one row and one column from a determinant of order n, we have a determinant of order n minus 1. Suppose we remove the row and column containing the element aij, so we are removing the ith row and jth column. We call the remaining determinant mij. The determinant mij is called the minor of aij. For example, let's consider this determinant, the minor of the element a23, so 2 or second row, third column, that's this one. Okay. Um, the minor is that when we remove the second row and the third column, the remaining elements 1 minus 5 2 1, we take the determinant of that. That gives us the minor m23. So we have 1 times 1 minus 2 times minus 5, that's 11. The signed minor, so if you include a sign which depends on the position, let's say minus 1 of I plus j are the indices 2 and 3 here, and times uh, the determinant m23 or the minor m23 or mij, that's called the cofactor of aij. For the element, this element here, a23, this the row is I equals 2, column j equals 3, so I plus j is 5. So you have the cofactor, which would be minus 1 to the power of 2 plus 3, which is 5, times m23, which is 11, so minus 1 to the power of 5 times 11, that's minus 11. To find the value of the determinant, we multiply each element of one row or column by its cofactor and add the results. And we can it can be shown that we get the same answer whichever row or column we use. For example, you evaluate the determinant of this using the elements of the third column. Okay, so if you write 1 minus 5 2 7 3 4 2 1 5, we take the determinant that's equal to, so we use the third column. So this is the first row and third column. So you have minus 1 to the power of 1 plus 3 of that number 2. And the minor would be, so if you remove this and this, you get 7 3 2 1. Okay, plus this number, so that would be 4 times negative 1, that's the second row and third column, so it's 2 plus 3. And then we remove this row and this column, you have 1 minus 5 2 1 times that number 4. Lastly, this one, which is minus 5, the position is third row, third column, 5 times the minor, which is derived, we get, remove this row, remove this column, you have 1 minus 5, 7, and 3. Okay, this becomes, so minus 1 to the power of 4, that's 1. So you have 2 here, times 7 times 1, minus 2 times 3, plus negative 1 to the power of 5. So that's negative 1 times 4 times 1 times 1, minus negative 5 times 2, plus, so this is 1 times 5 times 1 times 3, minus negative 5 times 7. Okay, and this becomes 2 times 7 minus 6, that's 1, minus, so this is 4 times 1 plus 10, that's 11, plus, so this is 3 minus um, negative 35, so that's positive 38. 38 times 5, so this is 2 minus 44 plus 38 times 5, that's 190. So 190 um, minus 44, that's 146 plus 2, 148. Some useful facts about determinants. If each element of one row or one column of a determinant is multiplied by a factor k, the value of the determinant is multiplied by k. The value of the determinant is 0 if all elements of one row or column are 0. This is easy to prove. Um, two rows are or two columns are identical. If they're the same, then the determinant is 0. Or if two rows or two columns are proportional, then the determinant is 0. If two rows or two columns of a determinant are interchanged, the value of the determinant changes sign. The value of the determinant is unchanged if the rows are written as columns and columns as rows, or if we add to each element of one row k times the corresponding element of another row where k is any number. Also, the same thing can be done on columns. Now let's use Cramer's rule to solve two equations and two unknowns. So um, we'll have a simple example of two equations and two unknowns. Um, we have this set of equations. One thing you can do, multiply first equation by b2 and second equation by b1, then subtract the results. Okay, so let's say this first equation multiplied by b2, that becomes a1 times b2x plus b1 times b2y equals c1 times b2. Here you have b1 times a2x plus b1 times b2y. So here b1 times c2, and then we subtract the two equations. Say we subtract the second from the first. This two cancels out. So you have a1 b2 minus b1 a2x equals, you have here C1 B2 minus B1 C2, or X can be written as C1 B2 minus B1 C2 over A1 B2 minus B1 A2. Similarly, we can do the same process to get, uh, we can get Y as, so Y is A1 C2 minus A2 C1 over A1 B2 minus A2 B1. If you observe, the denominators actually look the same. But here we can also write this in determinant form. Let's say the denominator can be written as A1, A2, B1, B2. The numerator you can write as C1, C2, B1, B2. Here you can do this A1, A2, C1, C2 divided by the same denominator here, A1, A2, B1, B2. So for the set of equations, we can write the solutions in this form. The denominator is called the determinant of coefficients, which we denote by D. So that's the coefficients of this x and y terms. So let's call this as our x coefficient, okay, and this as our y coefficient, or coefficients. This C1 and C2, let's call them the constant terms. So D, or determinant of coefficients, is derived by listing this x coefficients and y coefficients like this. To find the numerator of x, our numerator determinant for x, start with D, erase the x coefficients, replace it with the constant terms. Okay, so you remove A1 and A2 here, replaced by C1 and C2. For y, you replace the y coefficients, so the y coefficients of D, replace it with the constant term C. That's why you have this. Solve the set of equations. 2x plus 3 equals 3, x minus 2y equals 5. In this case, D would be 2, 3, 1 minus 2. So 2, 3, 1 minus 2. Okay, this would be 2 times minus 2 minus 3. So this is minus 4 minus 3, that's minus 7. Now the value of x would then be, so we start with this, but we replace 2 1 with a constant term. So you have 3 5 3 minus 2 divided by d. So 3 times minus 2, that's minus 6, minus 3 times 5, that's 15, over negative 7. This is negative 21 over negative 7. That would be 3, or x equals 3. Okay. For y, you start with d, replace the y coefficients with 3 and 5. So you have 2 1 3 5. 2 times 5 is 10, minus 3 times 1 is 3, divided by negative 7. That's 7 over minus 7. This is equal to negative 1, or y is equal to negative 1. Now another way of finding the rank of a matrix is by using determinants. So a submatrix is a matrix remaining if we remove some rows or some columns from the original matrix. To find the rank of a matrix, we look at all the square submatrices and find their determinants. The order of the largest non-zero determinant is the rank of the matrix. For example, we want to find the rank of the matrix, this matrix. Now we can observe things. So first of all, the largest square submatrix that we can find is if we remove one row, we get 3 by 3. matrix, but there are a lot of possible 3 by 3 matrices. Actually, there would be a total of, let's say, uh, several combinations of 3 by 3 matrices. Let's say we remove this, that is 3 by 3 matrix. If you remove this, there's another combination. If you remove this, another combination. Remove this. So there would be, apart from changing rows, there are three sub matrices that we can 3 by 3 sub matrices that we can derive from this. But observe that these two are proportional. So whatever matrix that contains these two, the determinant is 0. So if we want to find a non-zero determinant, we should just pick one of them. Let's say just this matrix, 3 by 3, or just this and this last two. Either of the two will give you um, a- the same determinant apart from a proportionality constant, because these two are proportional. So the determinant, let's say if we pick this matrix, the determinant of that would be -1 of the determinant if we choose times the determinant of when we choose this and these two columns. That is from our um, property number or property number one. If you multiplied one row by k, let's say if you have this, you multiply one column by -1, it would just be the same with this and this 3 by 3 matrix. So the determinant differs by a factor of -1. So whether it's 0 or non-zero, we can easily determine by just choosing one of these two matrices. So let's say we pick -1, 2, -4, 2, -1, 5, 3, 0, and 6. Okay, we can simplify this. You can start solving this, but we can simplify by using property number 4. That is, if we multiply this or we multiply this by some number, let's say -2, and then add that here, so that we replace this with the result. Um, Multiply first row by -2, then add to third row. So you have 2, -4, and -6. So that's the first row. And -4, 5, and 6. Okay, so this one here is -2, this is 1, and 0, which means that if you replace this by this, you'll get the same determinant. This is -2, 1, 0. Now this is easy to solve. So if we continue this here, we can choose for this row or this column. We can choose we can evaluate the determinant using this column, and there's only one non-zero term, that's 3. So we choose that. Um, that's -1. The position is first row, third column. The remaining element is 3, and then the minor would be, so if you crash this out, you have 2, -1, and -2, 1. Okay, so this is +1, 3. 2 times 1 is 2, minus -1 times -2, that's 2. So this is 0. What we get is rank is not 3. And in fact, More accurately, it is less than 3. Now it would be easy to show that it is 2, so we just pick any, we just pick um, a 2 by 2 matrix, which would, uh, there are there are some 2 by 2 matrices that would give you 0 determinant, but there are a lot of matrices, 2 by 2 matrices, that would give you non-zero determinant. Let's say, for example, this. So 2, 3, -1, and 0. The determinant is simply 2 times 0 minus 3 times -1. That would be 3, which is not equal to 0. Therefore, the rank is